In this video, we're going to be talking about DC to DC converters. So DC to DC converters are electronic circuits that convert a particular level of voltage, direct current voltage, to another level. So we can have a converter that converts 12 volts to 5 volts, or 5 volts to 12 volts. So basically the circuit works by switching, like by fast switching. So it turns on and off a particular switch, a switch in the circuit. So the average value of the voltage after switching, that will be your output voltage. So let's look at the circuit diagram. So this is a basic DC to DC switching converter, and this is when the switch is closed. So you can see when the switch is closed, the voltage in your source voltage is equal to your output voltage because the current is flowing through. Yeah. So let's take a look at when the switch is open. So you can see when the switch is open, there is no connection between your source voltage and your output voltage. So that means your V0 is equal to 0 because nothing is connected. So let's do some calculations. So from here, okay, let me show everything first so that I can show the output voltage graph. Okay, so this is your output voltage graph. When your switch is closed, you can see your V0 is equal to Vs, and this your dt is your duty cycle times time. So let me explain the equation. So this equation states that your output voltage is equal to your 1 over your total distance, but we are dealing with time, so that's 1 over t integral of your 0 to t. Yes, so that's your boundary of your V0 of t dt. So we're trying to find the average value of your V0 in this graph. So what you do is after this, you will now separate it, but like, let me write it out. So your V0 is equals to 1 over t integral of 0 dt, V0 of t dt plus 1 over t integral of your dt to your t, V0 of t dt. So when your switch, this is for when your switch is closed. So when your switch is closed, you can see your Vs is equals to V0. So if you replace this with your Vs of t, so your V0 will be equal to 1 over t integral of 0 to t Vs of t dt. So, and because when your switch is open, there is no, your output voltage there is 0. So that's why this whole thing here is 0. That is plus 0. So that's how we got this equation here. So, okay, so solving the integral, that's 1 over t vst, putting in your limits, you get this. Then subtracting your Vs times 0 will give you 0. Then you multiply it, your t, we can see your t. So your final, your average voltage value is VSD. And if you're wondering, your D is your, your D is your duty cycle. So let's find our change in time when it is closed. So when our switch is closed, our t will be 0. Our t our t will be dt minus 0. That will give us dt. And when your switch is open, your time will be yeah, it will be t minus dt. If you factor out your t, that's going to give you that. So your duty cycle, this is the fraction of time your switch is on compared to the total working time of the circuit. So that is your T on over T on plus T off. So this plus this, that will now equals T on over T. That's the value of your duty cycle. So there are different types of converters. We have bulk, we have the boost converters, we have the bulk boosts, which I'm going to be talking about later in this video. Okay, so the first type of converter we're going to be talking about is the bulk converter, which is also a step down converter. So for example, let's say you have a 12 volts DC, you can use a bulk converter to step it down to 5 volts. So how it works, let me zoom in on the circuits. Ouch. So how it works is, this is your main circuit. It has you have a source voltage, and this is your switch. So your source voltage, current flows through from your source voltage to your inductor when the switch is on. Okay, I'm coming. So it's close to your inductor when the switch is on. So if you don't know what an inductor is, it stores energy in magnetic field. So when your switch is off, your inductor then powers your system, yeah, your output voltage. So instead of burning the energy off as it's like using a resistor or using your linear voltage regulator, this rapid on and off switching of your circuits. I don't know how to explain. This rapid switching on and off of your switch, then I don't know how I explain this, but you get the idea. Switching on and off the circuits creates a voltage, and that voltage is then smoothened out with your by a capacitor. So instead of having ripples, you have just voltage. Okay. Now this is the circuit for when the switch is closed. So when the switch is closed, this side connects. So when they connect, you voltage here is equal to the voltage here. That's as I've written here. So then don't worry, we'll get to the analysis later. So when your switch is open, your voltage here is equals to 0 because there's no current flowing through this place. So now let's talk about the analysis of the circuits. So analysis for when the switch is closed. We are going to be using KVL, which says that the voltage, total voltage across the loop is equal to 0. So we have to take this, okay, something like this. So you have your Vx is equal to Vs, so you're going to take it. So there are different ways you can do it. You can take this sign first, like only pick this sign. So if you're picking only this sign, you also pick this sign and pick this sign. So I guess we all understand that for our KVL. So it will be, let's say we are picking the positive, so it will be Vs, then we are picking this side to minus VL, so VL, then we are picking this side to then minus V naught. So that is it. Let me put it on. So making your VL subject of formula, because we are trying to get the current flowing through the conductor. So at first we have to get the voltage. So the voltage flowing through the inductor will now be equals to Vs minus V naught. That's your output minus your inputs. Your input minus your outputs. So, and we all know that the voltage flowing through an inductor is equals to the value of your inductor multiplied by the differential of the current. So from here, you transfer your L under. So you have Vs minus V naught over L is equal to di L over dt. So from here, you can change your di to change in IL. So it's the same thing since we are finding the differential. So, and you also know that from what I explained earlier, that the time, the change in t of when the switch is closed is equal to the t from the graph I drew from that previous graph. That is your 0 and the t for when it's closed. So substituting this inside your formula after you have changed it, so you are substituting this inside. So you now have your Vs minus VL minus V naught over L is equal to change in IL dt. So from here, you have gotten your current flowing through the inductor when it's closed. So now let's do for the analysis. Let's get for the analysis when your switch is open. So for analysis for when your switch is open, we're going to find the KVL. So this is equal to 0 minus VL. Remember, we're picking this sign here. So there's a minus here. So that's minus VL minus V naught equals to 0. So as it, or you can pick that. So making your VL subject of formula, your V naught will go to the other side, change to negative. Then you also put in your value of your inductor voltage, the voltage of your inductor, which is L di L over dt. Then you bring your L inside. Basically what you did when your switch was closed. So then you substitute your value of your change in t. And remember that time that the value there was the t and t. So it was t minus dt, which gave us 1 minus d of t. So that is, so substituting this inside, you have your equation here. I hope we are all following. Yes, making this subject of formula, you already have your value of your current flowing through the inductor when your switch is opened. Okay, so next we are going to find the output voltage, like the output voltage of these circuits. So there will be times when it to be closed, times when it to be open. So we need to find our V naught, the value of our V naught. So to do that, we need to add the value of our currents when it's open and when it's closed. So let me bring out the values that were calculated earlier. So the currents flowing through the inductor when it's closed and when it's open, when you add them together, it's going to give us 0. So I think that needs no further explanation, but putting the equation now, you have Vs minus V naught over L dt minus V naught over L 1 minus d t equals to 0. So from here, to simplify it, just bring out your T and L. So your T is common, your L is common. So bringing it out, you have Vs minus V naught D minus V naught 1 minus D equals to 0. So now your T over L will be equals to 0 from our basic algebra. Okay. So then you open the brackets, VSD minus V naught D minus V naught plus, this will multiply this, minus V naught will multiply minus D. You understand? Minus will give you a plus V naught D. So from here, you're okay. This will cancel out. Yes. Positive V naught and negative V naught will cancel out. So then you have your VSD minus V naught equals to 0. So therefore, the output voltage is equals to your source voltage multiplied by your duty circuit. Yeah. So next thing we are going to calculate now is the inductor current. Yeah, the maximum inductor current. So we are going to need all these things when we are designing the circuits, when we are trying to find the value of the particular value of inductor to use for your circuits to meet your need. Okay, so let's start by finding our KCL. So looking at it from here, you can see your IL is flowing through this. Let me just draw it out. So this is your IL, and this is IC, IR. So from your KCL, yes, Kirchhoff current law, you know that our IL, like current flowing through, is equal to current flowing out of the node. This is our node. So yeah, IL will be equal to IR plus IC. So okay, but your IC here is equal to 0. Yeah, the value of your the current flowing through your capacitor is equal to 0. So that means your IL will be equal to IR. So that's equal to V naught over R. So from here, the current yeah, so the current flowing through this your load here is V naught over R, like from your Ohm's law, V equals to IR. So this is your output voltage and this is your load resistance. So then the value of your Imax will be equal to this. I'm coming. Okay, so before we move on, because this is looking kind of, let me explain why this is the formula we're using to calculate our maximum currents. Let me draw a graph for us to see. So during the on and off cycle, this is what goes on in the current of this is our IL, current of our inductor. So this is your minimum current, inductor current. So when the switch is closed, the inductor charges up, like energy is stored. This is your maximum current. Then when the switch is open, the energy leaves the inductor. So that's the cycle repeats itself. So then this is now like half of it. So this is your Imax and this is your Imin. And this here is your DT, from the graph that I've drawn before. And this is your T. Then your IT is your change in IL. change in inductor current. So that's why we're the Imax is your IL plus half of, because we know we are dealing with Imax. So half of this, half of your change in IL. So that's why we are using this formula. And we're also using change in IL because we are dealing with when the switch is open. That's when the inductor is discharging. Okay. So your IL is equal to V naught over R from what we explained here, plus 1 over 2, and our change in IL from what we calculated when the switch is open. Then factoring out our V naught is common, so take V naught out. You're left with 1 over R plus 1 plus D T over 2L. And the reason this is F because T is equal to 1 over F. Okay, so let's move to our Imin. That one will just be subtraction. So it will be your IL minus change in IL over 2. So the same thing we did here. So factor out your V naught. Okay, this is meant to be minus. Okay. So now we need to find the smallest inductor value. Like the smallest inductor, I mentioned about that we need all these parameters when we are designing our circuit. So to find the smallest inductor value for the circuits, we need to equate our minimum current equals to 0. So your Imin will be equals to 0. So you equate everything you got here to 0. It's meant to be minus here. So yes, this is it. So from here, your V naught is equal to 0 automatically. Then you bring this to the other side. Then you have 1 over R is equal to 1 minus T over 2 LF. So making your LF subject to formula, so your minimum LF will be equal to 1 minus T over 2. So from here, if you bring your F back to this place, if you bring your F back to this place, so therefore your minimum inductor will be equal to 1 minus D multiplied by R over 2F. So next we are going to calculate the output voltage ripple. Okay, so let me explain how to get our output voltage ripple. So from the circuit diagram before, that this is your IL and your IR, IC. So that's how we came about this equation here. So this is meant to be over 2. So to calculate the charge here, our change in Q, we have to find the area of this triangle, and the area of triangle is equal to half base times height. That is 1 over 2 times our base is T over 2 multiplied by your change in current over 2. So multiplying this, that will be 2 times 2 times 2, that's 8. That's T change in IL over 8 is equal to your change in Q. That's what you have here. So, and also know that your charge is equals to your capacitor times the output voltage. So that means your change in Q will be equals to C multiplied by change in V naught. So now equating this into this, what are we going to have? We're going to be having change in Apologies. So making our V naught subject of substituting our change in Q with this, we are going to have V naught, change in V naught is equal to change in Q over C. Okay. So that's what we did here. And our change in Q is equal to T change in IL over 8 multiplied by 1 over C. Then you have this. And also remember that your IL, the change in IL is that we solved earlier is equals to Vs minus V naught over L dt. And your source voltage, remember your V naught is equals to Vs t. That's what we solved when we added our change in IL or for closed and open. So substituting your Vs this inside this, then you have V naught over D minus V naught over L dt. That's equals to, and multiplying this, your D will cancel out this D, then to be minus V naught D. So V naught minus V naught D over LF. The reason we have F, like I've mentioned before, your T is equals to 1 over F. Yes, so substituting that, and your V naught is common, so you factor it out. So your V naught is, so your change in, no, so your IL, change in IL is also equals to V naught open brackets 1 minus D LF. So we are now going to substitute this thing here. Just substitute it inside here. So let's do that. So now we say substituting it inside, you have T over 8C multiplied by V naught into brackets 1 minus D over LF will be equals to this. The reason we have F square is because of your T is also 1 over F. So the F will multiply the other F to form square. So 8C LF square. That's it. And you can also write it as your change in V naught over V naught is equal to 1 over D over 8LCF squared. But note that your change in V naught is your output voltage ripple. Yeah. Okay. So I think that's all for the analysis of buck converter. Now let's solve an example on that. So, okay, let me paste the question. This is an example on buck converter. A buck converter has the following properties. Your Vs is equal to 24 volts. Your DC circuit 0.65. Your inductor is 25 microhenry. Your resistor is 10 ohms. Your frequency is 100 kilohertz. Your capacitor is 15 microfarad. So let's solve it. And we're asked to find the output voltage, maximum and minimum inductor currents, output voltage ripple. So what we basically have to do is just to remember our formula that we've gotten like previously. So let's solve the first one, our output voltage. And what is the formula for output voltage? V naught is equal to VSD. And what's our VS? 24 multiplied by 0.65. So if you plug that into your calculator, you arrive at 15.6 volts. So that's all for your output voltage. Then to find your minimum and your maximum and minimum inductor current, you also have to remember the formula, where you can derive it again if you forgot. So your Imax is equal to V naught open brackets 1 over R plus 1 minus D over 2 LF. So substituting your value, your V naught is 15.6, your R is 10 ohms, your D is 0.65, Your L is 25 microhenry. Your F is 100 kilohertz. So writing it out. Then if you plug this inside your calculator, and also remember that your micro is 10 raised power minus 6 and kilo is 10 raised power 3. So because if you make a mistake in this area, you miss your final answer. So plugging this inside your calculator, you should arrive at 2.652 ampere. So same thing with your minimum. Once you have this formula, you know the only thing you need to change is the sign. So that's what the change there. So plugging it in, your 15.6 1 over 10 minus 1 minus 0.65. Plugging this inside your calculator, you arrive at 0.468 ampere. That's your minimum inductor current. Then to find your voltage ripple, same thing. Know your formula, which is change in V naught equals to V naught open brackets 1 minus D over 8LCF square. Substituting your V naught is 15.6, your D is 0.65, your L is 25 microfarad. So you can also try this, pause the video and try calculating this yourself and see if you arrive at the same answer. Okay, so putting in your values, you should arrive at 0.182 volts. So that is an example under buck converter. So next we're going to be talking about boost converter. So this is boost converter from the name. It boosts voltage levels. Let's say you have 5 volts, it can boost it up to like 12 volts, something like that. So the way it works is it charges up the inductor. Then when the inductor is done charging, it now releases the energy. The inductor then releases energy to the output voltage. So okay, what's the best way I can explain it? So the thing is that when the energy that is stored in the inductor, the voltage is stored at a higher voltage. Yes, so let's say it's your VS is 5. It can be storing your voltage in like 12 volts. So that when it's releasing its energy to this circuit, your V naught will be greater than 5 volts. So I hope that explanation is correct. So, and the purpose of this your diode is to prevent current from is to make current flow in one direction. So when your switch is open, your voltage is your capacity, your inductor is charging. So your inductor is then connected to the ground. This makes your diode reverse bias. So the voltage here will be equal to 0. And prevents your capacitor from discharging through the inductor. Yeah. So and when it's open, you can see there's nothing here. When it's open, your inductor flows to your output voltage. It discharges. Okay. So now let's analyze for when the switch is open and when the switch is closed. So we are going to also use KVL, but I think it's not compulsory because looking at it, you can see this is your VS, your ground. This is also your VL ground. So that means your VS is automatic. Your VL goes to your VS automatically like that. So your VL is equals to VS, and the inductor, your inductor voltage is equals to L DIL over the thing. So basically what we did in our bulk converter. So now you convert this to change in IL. So and we know that your change in T for when it's closed is equal to dt. So you substitute your value, you substitute this inside, then therefore your change in IL when it's closed is equal to Vs over L dt. So we are going to use the same approach when analyzing for when the switch is open. So when the switch is open, okay, let's find the KVL of that. So this is Vs minus VL minus V naught equals to 0. So if you make your VL subject of formula, you have this. If you make VL subject of formula, it will be Vs minus V naught. So your VL will come here. So also equating it to your inductor voltage, L DIL over dt, and bringing your L, dividing both sides by L, and changing this to change in IL over change in T. And for when your switch is open, your change in T is 1 minus D multiplied by T. Substituting that, you have this. Then your change in IL for when your switch is open will be this equals to Vs minus V naught over L 1 minus dt. So next you should be able to guess what the next one is. To find our output voltage, our average output voltage. And to solve that, we have to add our change in current for when it's closed and when it's open. So let's write it out. This is what we got when it's closed and when it's open. So we'll add these two together. Equating this will give us 0. So substituting it. And from here, your T is common and your L is common. So you factor that out. So you have VSD plus VS minus V naught minus VS. So let me break it down. So your Vs minus V naught multiplied by 1 minus D. So that is Vs times 1 Vs minus Vs times D, VSD. V naught times 1 minus V naught minus times minus plus V naught D. So that's how we got this aspect. So your T over L will be equal to 0. And let's write that out. So from here, our VSD cancelled out because of this plus or minus. No. So making your V naught subject of formula, you bring your Vs to the other side. So factoring out your V naught, you have V naught 1 minus D equals to Vs. So dividing both sides by 1 minus D, your V naught will be equals to Vs over 1 minus D. So that's your output voltage. Okay, so next we have to find our IL. So this one will be different from the way we did it in our when finding for bulk converter. So for this one, we are going to be using our output power and our input power. So we're going to be equating our output power to our input power to find our IL. So what is your output power? Your output power is equals to V naught over R. So your output voltage divided by your load resistance. So, and from here, we know that okay, let me just separate it. So your V naught over R. Okay, yeah. Let me just say your V naught is equals to I naught R. So from Ohm's law, so that means it will be V naught I naught R over R. So your R cancels. That's how you get V naught, I naught. And our input power, PS. What is that? Our PS. Our PS will be equals to VS IS. And your IS is equals to your IL. Because see, this is your IL. This is your IS. And this is your IL. So the current is the same thing. So your IS equals to IL. Okay. So now we are going to equate our input power to our output power. So this equals to this. So our VSL equals to V naught over R. So from here, we are trying to find IL. So we'll make IL subject of formula. So we'll bring our VS down. So, and also we can substitute value for V naught. Our V naught square is equal to V naught I naught R from what I've explained earlier. Okay. So your R will cancel, basically this one substitutes inside here. So this is your value of your IL. Or you can use another, let's say you don't want I naught and VS values to be like together. You want everything to be VS. So what you do is from your from what you got the output voltage, your output voltage is VS over 1 minus D. So you substitute this is your V naught inside. Yeah. Sorry, inside. You substitute this V naught inside this place. So substituting this inside, you have VS square IG square multiplied by 1 over VS R. So this one will cancel your square 1 over. So that means your IL will be equals to VS over 1 minus D square R. So now we have found our IL. Next thing we need to do is find our maximum currents flowing through the inductor and our minimum current. So this should be easy. So from the formula, our maximum current, I explained how we came about this when explaining buck converter. So substituting your values. So from what we calculated earlier, our IL is equals to VS over 1 minus D square or square R plus our IL. And note this is your IL for when the switch is when the switch is closed. So next thing, your Imin, that one you just be introducing your minus instead of plusing. So VS dt over 2L. Okay, now we have to find our minimum inductor value to find your L min. So your L min, your I min, sorry. To find your L min, you equate your minimum current to 0. So this equals 0. So bringing this one to the other side, you're going to have VS over 1 minus D all square multiplied by R equals to VSD over 2LF. Note that this has changed to 1 over F. So that's why it's F there. So from there, you are going to you just bring your LF to this other side and bring every other thing down. So your LF will be equals to your D and your VS is cancelling out because this from our normal algebra. So it cancels out. So sum will be 1 over 1 minus d square r equals to 1 over 2 LF. So making LF subject of formula is equal to this, but we are mostly concerned about our inductor. So your F will go back down. So that will be D open brackets 1 minus D all square R over 2F. So that's the value of our inductor. Next, we're going to be talking about this. So to find our output voltage ripple, like our charge, we have to look at the two conditions and look at when the capacitor is discharging. So you can see when the switch is closed, you have DC. When the switch is open, you have 1 minus D multiplied by T. So, and when the switch is open, you can see that the inductor current is actually flowing into your load. But when the switch is open, it's the capacitor that is discharging. Like is actually drawing current from the capacitor. So your I naught is coming from your capacitor. So to find your output voltage ripple, the charge will now be equals to V naught over R multiplied by dt. And we already know this from what I solved in buck converter, that your charge change in Q is equals to your capacitor multiplied by change in V naught. So equating these two together, you have this C change in V naught equals to V naught dt over R. So we are making change in V naught subject of formula. So your C will come down. So then you have change in V naught equals to V naught dt over RC. So you can also write it like this because your T is 1 over F. So, and you can also bring your V naught down to write it this way, diversity. So now let's look at an example on boost converter. So we're going to apply all the formulas we learned. So the question is this. A boost converter has the following parameters. Vs is equal to 20 volts, duty cycle is equal to 6. Your resistance is 12.5 ohms. Your inductance is 10 microhenry. Your C is equal to 40 microfarad. Your F is 200 kilohertz. And we are asked to find the output voltage, the average minimum and maximum inductor current, and your output voltage ripple. So, and before we start, our average inductor current is IL. So we already derived that previously. So let's start with our output voltage. So your output voltage formula is V naught is equal to Vs over 1 minus D. So inputting your parameters, your Vs is 20, your D is 0.6. So you have 20 over 1 minus 0.6. So go ahead and punch your calculator. And yeah. So you should arrive at 50 volts as your output voltage. So you can see that this is boosting your voltage from 20 volts to 50 volts. Next, let's find the average inductor current. So average inductor current is IL, which is equals to V naught square over Vs over R. And the other formula for IL that we derived is Vs over 1 minus D square R. So you can use either formula, you're going to arrive at the same answer. So now substituting your parameters inside, you have 50 square over 20 times 12.5. So punching your calculator, you should arrive at, yeah, what's the answer? Yes. Your answer should be 10 ampere. So now let's find our change in IL. So we are going to need that when calculating our Imax and our Imin. So formula for changing IL, that's Vs dt over L. And your T is 1 over F because it's F that we're given. Yeah. So our formula for, substituting your parameters inside, you have 20 times 0.6 over 10 times 10 raised power minus 6 times 20 times 200 times 10 raised power 3. So also, again, be mindful of your units so you won't make any mistake. So that's equals to 6 ampere. So now writing our formula for maximum current, your IL plus change in IL over 2. So we already found the values, so we just have to input them. That will be 10 plus 6 over 2. So this you don't really need calculator. Well, yeah. 10 plus 6 over 2, your 6 over 2 is 3, so that's 13. Then your I mean, you change this into minus. So that will be 10 minus 3. That will give you 7 ampere. So next, we have to find your output voltage ripple. And the formula for output voltage ripple is change in V naught is equal to V naught D over RCF. So inputting your parameters inside, you should go ahead and try it yourself first. So that should give you, inputting your parameters, you have 50 times 0.6 over 12.5 times 40 times 10 raised power minus 6 times 200 times 10 raised power 3. So after punching your calculator, you should arrive at 0.3 volts. So this is your output voltage ripple. So next, we are going to be talking about buck boost converter. So this is like the combination of buck and boost converter. This is the circuit for buck boost converter. So you have your switch, your inductor, your diode, your capacitor, and your load, which is here. So when your switch is open, you can see it's only your capacitor is charging into your load. So your inductor is charging from your output voltage. So when your switch is open, you can see your inductor current is flowing into your load. And let's look at the direction. See, it's flowing back here. So you actually have minus V naught, but we'll get to that in a minute. So now let's find the analysis. Let's analyze for when the switch is closed. So analyzing for when the switch is closed, we'll find the KVL. But I don't think we need KVL. From here, the VS is equal to VL. So VL is equal to VS. So and your inductor voltage is equal to L DIL over dt. So from what we've been doing back, you should be able to solve this part yourself. So you can try it on your own. So moving on, you move your L down, divide both sides by L, then you change it to change in IL, and know your change in T is equal to dt. Substitute that inside the equation. You have Vs over L equals to change in IL over dt. Then making your change in IL subject to formula, you arrive at your current, your change in current when the switch is closed. That is equals to Vs over L dt. Now let's find the analysis for when the switch is open. So when the switch is open, your VL is equals to V naught. So because they are connected in parallel, so the voltage here will be equals to the voltage here. So your VL is equals to V naught. So equating that to your inductor voltage formula, L di L over dt, then dividing both sides by L, you have V naught over L is equal to the differential of your current, inductor current. Then substituting your value of change in T, which is 1 minus D multiplied by T. Then you arrive at V naught over L is equal to change in IL over 1 minus D multiplied by T. So from here, you can make change in IL subject of formula to arrive at your answer. So this is your change in IL when the switch is open. V naught over L 1 minus D of T. So now we have to find the average output voltage. The average voltage, which is the output voltage V naught. So to do that, we are going to add our current. So of our change in IL when it's closed and when it's open. So let me write it out. This is when it's closed, when it's open. We're going to add it together. So adding it together, you have this Vs over L dt plus V naught over L 1 minus T multiplied by T. So from here, you can bring out your T and L is common. So you can bring out your T and L. So you are left with VSD plus V naught minus V naught D. So from here, you can make V naught subject of formula. Let's bring it out. Make V naught subject of formula. Your VSD will go to the other side. Then factor out your V naught. Then divide both sides by 1 minus D. So you now arrive at V naught is equal to minus Vs open bracket D minus 1 minus D. So next thing we have to find is your currents, your average inductor current, your IL. So just like what we did for our boost converter, we are going to be using our output power and input power. What is the output power? Your output power is V naught over R. And input power, P of S, is Vs Is. But your Is is equal to IL T. So because of your switch, that is here, that's why you're multiplying it by D. So from there, your VSILD is equal to your PS. So now equating your input power to your output power, you have VSILD equals to V naught square over R. So making your IL subject of formula, you now have VL is equal to V naught square over VS RT. So you can substitute, you can use this formula, but you can substitute the value of your output voltage you got previously, which is minus Vs D minus 1 minus D. So substituting that inside, you arrive at Vs square and D over 1 minus D all squared. From here, your Vs will cancel your square. Your D will cancel your D. So you will left with 1D. So this is what you arrive at. So this is the value of your average inductor current. Next thing on the list is to find our maximum inductor current and minimum inductor current, your Imax. So your Imax is equal to IL plus change in IL over 2. So with the IL we found earlier, VSD over R open brackets 1 minus D all square plus what is your change in IL? That's VSDT over 2L. So we are using it for when it's closed because that's when the capacitor is charging. So now for our Imin, just like what we did, it's just the negative that is changing. You arrive at this. So from here, you can actually factor out your Vs and your D to give you Vs, D, open brackets 1 minus R power 1 minus D square plus C. You can just do 1 over 2 LF. So you can leave it like this. So now we have our outputs, our maximum current and minimum current. So now what is left for us is to find the minimum inductor value for the circuit. And to find that, you equate your minimum inductor current to 0. So your Imin is equal to 0. You bring this to the other side, get this. And note that your Vs will cancel, your D will cancel. So you're left with 1 over R open brackets 1 minus D square equals to 1 over 2 LF. So you can make LF subject of formula to get R open brackets 1 minus D close the bracket square over 2. So then now you bring your F down to get your minimum inductor to be R 1 minus D all square over 2F. So that's your minimum inductor current. Minimum inductor value. So now we have to find the output voltage ripple. This one will be similar to that of your boost converter. So I'll be brief while explaining. So we know when the switch is open, the capacitor is discharging, so the current is flowing to the load. So that's why our change in Q is equals to V naught over R multiplied by dt. So you're changing C. Yeah. So which is equals to C change in V naught. So bringing that out and making change in V naught subject of formula, you arrive at this. So you can make your T to be 1 over F. So that's V naught D over RC F. Then you can also write it if you want to bring your V naught under. So the reason their output voltage ripple is the same is because of for both of them, for both circuits, for both buck for both boost converter and buck boost converter, when the switch is open, the capacitor is discharging for both of them. That's why the output voltage ripple is the same thing. So let's solve a problem on buck boost converter. But before that, I want to note something that for your buck boost converter, to know when it's in buck mode or boost mode, because you know they are the combination of two. So when your D, that's your DC circuit, is less than 0.5, that means it is in buck mode. So that means the switch is closed less than half the time. So the output voltage will be smaller than the input voltage. No, bulk is stepping it down. But when your D is greater than 0.5, let me just write this properly. So when your D is greater than 0.5, it is in boost mode. So the switch is closed more than half the time. So the output voltage will be larger than the input voltage. That's in boost mode. So, and which other thing? There is also another thing to clarify. The reason we have negative output voltage, like your V naught is negative, is because if you put in a positive voltage, let's say you put in 12 volts as a source, you'll be getting negative voltage. So you'll be getting -5, -24 volts. for your buck boost converter. So now let's solve the example. Yeah, this is what I explained earlier. So this is an example. Said a buck boost converter has the following parameter. Vs is equals to 12 volts, D is equals to 0.6, R is equals to 10 ohms, your L is equals to 10 microhenry, your C is equals to 20 microfarad, your F is equals to 200 kilohertz. Then we have to find the output voltage, the average, maximum, and minimum inductor current, and voltage ripple. So let's solve that. And if you like to solve this yourself, you can pause it and use the formulas we have derived previously to attempt this yourself. Okay. So first, let's find our output voltage. Our output voltage V naught is equal to minus Vs multiplied by D over 1 minus D. So inputting your parameters, your 12 volts is Vs, your D is 0.6. So okay, let's find the answer first. So inputting your values, you get minus 18. So remember what I said about when your D is greater than 0.5. So you can see your D is greater than 0.5. So that means it is a boost converter. Yes, boost converter. That's why you see the voltage is increasing from 12 volts to 18 volts. Next, let's find the average, minimum, and maximum inductor current. So your IL from where we solved is VSD over R open brackets 1 minus D square. So you can also use the other formula. What's the other formula? That's Vs square. No, sorry, V naught square over Vs RT. So if you use this formula too, you can arrive at the same answer. But let's use this. So substituting your values, you have 12 times 0.6 over 10 open brackets 1 minus 0.6 square. So your final answer will be 4.5 ampere. So next, let's find our change in IL so that we can substitute it inside our maximum and minimum inductor current formula. So your change in IL is equal to VSD LF. So where's your VS? Your VS is 12, your D is 0.6, your inductor is 10 microhenry. I'm sorry if okay, that should be it. So that's it. So substituting it inside your formula, you should arrive at 3.6 ampere. So the formula for your so substituting your IL and changing IL values, then you have 4.5 plus 0.6 over 2. Then punching in your calculator. I think you should be able to do this with hand. Yes. So 2 divided by 3 is 1. I mean that 1.8. Yeah, 2 in 16 is 8. So 1.8 plus 1.5, that will be 6.3 amperes. So yeah, 6.3 amperes. So your Imin, so that will be 4.5 minus 1.8. That will give you 2.7 ampere. Now, the next thing is to find your voltage ripple. Formula for your voltage ripple is V naught D over RCF. Then if you input your parameters, 18 times 0.6 over 12.5 times 20 times 10 raised to the power minus 6 times 200 times 10 raised to the power 3. Yeah, final answer would be 0.216 volts. So this is all on DC to DC converters. There are also other types of converters, but um, I'll be talking about that later. So if you have any questions, leave a comment down below. Thank you for watching.